For decades, database architecture relied on a single powerful server holding structured relational tables. But as modern applications generate petabytes of data, scaling vertically by adding more CPU and RAM hits a strict hardware limit. The monolithic structure eventually shatters under extreme data loads. To bypass this physical bottleneck, engineers developed NoSQL. By abandoning rigid predefined schemas and complex multi-table joins, the database can distribute its workload across a cluster of commodity servers, a process known as horizontal scaling. Dropping the relational table format creates an immediate engineering problem. Without rows and columns, database architects have to decide exactly how much structural awareness the new storage engine should retain over the data it holds. Horizontal scaling is not a simple software upgrade. It is a strict hardware compromise that requires a complete redesign of how data is physically arranged on a storage drive. That redesign split NoSQL into several architectural categories. Today, we are evaluating two distinct approaches to this problem: the key value store, utilized by engines like Redis, and the wide column store, built into systems like Apache Cassandra. These two systems are built for entirely divergent operational goals. One is optimized to maximize absolute frictionless retrieval speed. The other is engineered to ingest and analyze continuous, high-velocity data streams. A database cannot perform a software trick to bypass its hardware. Its performance capabilities, read speeds, and analytical limits are strictly dictated by the physical anatomy of its storage layer. To understand why a key value store operates so differently from a wide column store, we have to look past the marketing terminology and examine exactly how each engine handles a raw data payload. In modern system design, matching the precise physical data structure to your application's query pattern is the definitive engineering skill. The key value store is the simplest architectural subclass of NoSQL. Conceptually, it operates as a massive distributed hash table consisting of unindexed hairs, a unique locator name, and the data it points to. This diagram illustrates why this architecture is exceptionally fast. Because the locator provides the exact memory or disk hash location, retrieving a record executes in O1 constant time complexity. The network instantly isolates the path to a single value block, regardless of how large the database grows. But look at how the engine treats the value itself. The database treats the payload as an opaque blob. It stores the value and returns it upon request, but it does not parse, inspect, or understand the internal properties locked inside. This creates a state of severe structural blindness. Because the payload is opaque, the database engine cannot index individual fields or search for specific attributes within the blob. We can test the limits of this architecture with a standard analytical query. Imagine asking the database to calculate the average age across a user base of 1 million records. In a relational database, the engine would scan an age column, but here, the age data is locked inside 1 million opaque blobs. The database storage layer has no native way to filter or read that data. This diagram shows the resulting system failure. To calculate the average, the application layer is forced to request all 1 million opaque blobs, dragging the entire dataset over the network to parse the values manually in the application's memory. This brute force extraction process incurs a massive CPU penalty and triggers severe network latency, effectively paralyzing the system. The key value architecture intentionally sacrifices complex analytical query capabilities to guarantee frictionless, high-speed point lookups. When engineers needed to execute complex analytical queries across massive distributed clusters without returning to rigid DBMS tables, they built the wide column store. This animation illustrates the mechanical solution. To regain structural awareness, the wide column architecture breaks open the opaque blob and separates the data attributes into distinct segments. These independent strips are organized into the core structural unit of this architecture, the column family. Columns that are frequently queried together are grouped under a single row identifier. Unlike a strict relational table, these rows are dynamic. A single row within a column family can contain a completely different number of columns with entirely different names than the row directly beneath it. This flexibility solves the sparsity problem found in legacy databases. If a record lacks data for a specific field, that column is simply omitted from the row, consuming zero physical disk space for null values. To understand how this works across a distributed cluster, we must isolate the internal anatomy of a single wide column data cell. Looking at this exploded view, every individual cell physically contains three mandatory components: the name, which acts as the key, the value payload, and a timestamp. That timestamp is a critical engineering feature. Wide column stores like Cassandra use a masterless peer-to-peer network. Because any node can accept a write request, the database uses these cell-level timestamps to natively resolve data conflicts without relying on a central coordinating server. By reintroducing explicit internal structure, wide column stores allow the engine to scan targeted attributes while maintaining the ability to scale horizontally across thousands of nodes. Logical software structures only explain half the performance equation. The true advantage of a wide column store becomes apparent when we observe how it physically writes data to the hardware. Notice how the mechanical read head in this traditional row-based drive behaves. To read a single column of data across multiple records, the disk arm must jump randomly across the spinning platter to collect scattered attribute blocks. These random disk arm seek movements generate severe mechanical latency, creating a hard physical limit on how fast the database can return analytical results. Watch what happens when the disk layout reorganizes into a wide column format. Identical data attributes are grouped and written in long, contiguous blocks directly onto the disk. When an application queries a specific metric, like user age, the read head skips directly to that continuous block, scanning it rapidly while completely ignoring names, addresses, and irrelevant fields. Storing identical data types in sequence provides a secondary engineering advantage: massive efficiency in data compression. Compression algorithms operate by identifying repeating patterns. When a system compresses an unbroken sequential string of similar data types, like thousands of integers in a row, it reduces the physical storage footprint far more effectively than compressing mixed text, dates, and numbers in a standard row. To handle incoming data, these systems utilize append-only write logs. By writing new data sequentially to the end of a file, the engine eliminates disk seek times entirely, seamlessly ingesting high-velocity data without dropping records. Wide column performance relies on forcing the physical hardware storage layout to perfectly match the analytical access pattern of the query. With the mechanical behaviors of these storage layers clearly defined, we can map them directly to the industrial use cases they were built for. There is no universal, superior NoSQL database. System architecture dictates that you select the engine that explicitly matches your application's data access pattern. If an application demands sub-millisecond point lookups and retrieves entire objects using single unique identifiers, the key value store's opaque blob is the optimal choice. In production, this architecture powers volatile user session management, massive in-memory caching layers, and high-speed network routing tables, where analytical filtering is entirely unnecessary. Conversely, if an architecture requires high-velocity write capacity, absolute partition tolerance across data centers, and the ability to scan specific attributes rapidly, the wide column store is required. This split screen represents the architectural divide. Key value rules the high-speed caching tier, while wide column handles the heavy ingestion required for globally distributed IoT sensor telemetry and continuous system logs. The decision rests entirely on the trade-off between the absolute frictionless speed of an opaque payload and the complex, targeted analytical awareness of the column family. In advanced distributed systems, high performance is the inevitable mathematical result of aligning physical data layout on a disk with the specific behavior of the application above it.